Welcome. Today topic is magnetic moment. That is represented by this. And first, if you look the definitions, what is magnetic moments? Okay. So if I define it, then we say that it actually refers to the strength of the magnetic field or orientations of a magnet or any object that produces a magnetic field, essentially indicating its orientations. It's aligned with the external magnetic field. So it refers to that. It refers to the strength or orientations of the magnet or maybe any object that produce magnetic field, and indicating essentially, we can say essentially indicating its tendency to align with the external magnetic field. Okay, so magnetic moments, it generally refers to the strength or orientations of a magnet or any object that produces a magnetic field, essentially indications its tendency to align with the external magnetic field. That is called the magnetic moment. Okay, or also we can say that it is the product of poles and distance between the poles. Okay, and it is vector quantity. It means that we have to consider both magnitude and distance. So magnitude and that is directions is considered. Okay, and how it works actually. So this how it works, this magnetic moments. So if you say that if any when in a placed magnetic field, an object having magnetic moment when in a placed magnetic field, an object having magnetic moment experience a torque that tries to align with the external magnetic field. Okay, so when in a magnetic field, if you place any objects that having a magnetic field, a magnetic moment, then it experiences a torque, and that torque that tries to align with the external magnetic field. So in this way that this magnetic moment it works. So how it's in atomic level, if I talk about talk of atomic level, then the spin and spinning and orbital motions of the electron around the nucleus play a crucial role. Okay, the spin and orbital motions of the around the nucleus, motions of the electron around the nucleus plays a crucial role. Plays a crucial role. Okay. So what is the applications of it? Applications is, we can say that MRI, that is magnetic resonance imaging. Here we use that this magnetic movements. Okay, so these are all about of that what is magnetic movements, how it is works, and what is its applications. Although these things in net exam will not come, so I just going to give this introduction. So how actually, what do you mean by magnetic movements, why it is necessary, and how it works, and what do you mean by magnetic movements. Okay, so now we will discuss what actually come in the exams in CSR, net or GATE, that is how to calculate the magnetic moment. Okay, this magnetic moments that is represented by this. Okay, this can be, we will study it for the two case. One is for that heavier elements, another is for that lighter elements, another is for lighter elements. Okay, now we are discussing about of the calculations of magnetic moments. Okay. For heavier elements like lanthanide cases, and lighter elements like transitions metal complexes, transitions metal cases like 3D series. Okay, so for heavier elements, how to calculate this magnetic movements? Magnetic movement that is represented by this sorry, this is calculated by, that is G into this multiplied by J upon J plus 1. Okay, that is J into J plus 1, where J is Landau splitting factor, where J is Landau splitting factors factor, and J is, we know that what do you mean by J, that is spin orbit coupling, that we have already discussed, spin orbit coupling. Okay, so generally for heavier elements that spin orbit coupling is considered, and for lighter elements spin orbit coupling generally that is neglected. Okay, so here for heavier elements, spin orbit coupling is considered and here that spin orbit coupling is generally neglected. Okay, so now we will discuss that how to calculate that magnetic moments for heavier elements. After that we'll go for that lighter elements. Okay, so first we will discuss on that heavier elements. The calculations of magnetic moments, that is represented by this, for heavier elements. Okay, so for this, so what is the formula for calculating that magnetic moments? Formula is lambda factors G into spin orbital coupling, spin orbital. Okay, this J is I said that there is lambda factors, and this J, for the formula of J is, we can do that S into S plus 1 minus L into L plus 1 upon 2J J plus 1. For calculating this J, we have to use this formula, and that J is, we know that this is the spin orbit coupling, so we see that this is the summations of this is L1 plus, that we have discussed, this is L1 plus S1 dot L1 minus S1, sorry, yes, L1 minus S1. Okay, this is the J values that we have already discussed these things while we are discussing on calculating the terms and term symbols. Okay, so now let's take the examples. If I take about of heavier elements, that is like lanthanide compounds. So let's take, and that lanthanide compounds generally have that F block elements, let's say for F2. Okay, for this case, here if you fill that electrons, then 1 2 3 4 5 6 7, its value is 3 2 1 0 minus 1 minus 2 minus 3. Okay, so 2 electrons are there, 1 and 2. So we know that how to calculate the values of L. Also that how to calculate the L value. So L, whenever one orbit is there, then always L is equal to summation of ML values or L values. If you take this is L value, then summations of L values. Okay, so this is 3 into 1 electron plus this is 2 into 1 electron, that is going to be 3 1 is 3 plus 2, that is going to be 5. Okay, similarly if I calculate for S is, since there's one orbit, the summation of S values. So here this is half, we will calculate only for that unpaired electrons, because for paired electrons that will cancel out. Okay, so this is half plus half, that is going to be 1. So S is 1. Okay, and what things we know that for J value, that is L1 plus L2, sorry, L1 plus S1 dot L1 minus S1. This is, let's say, L1, this, let's say, S1. Okay, so we say that whenever this is a half filled, okay, and it is in a one orbit, so if it is single orbit is there, single, or we can say that whenever it is half filled, now we will look that which value we will take. Suppose this is 5 and 1. Okay, so for this kinds of, if it is 1 orbit, then how we will take that? We will look that whether this is half filled or fully filled. Okay, if it is less than half filled, then on that case L minus LS is taken. Okay, and if it's more than half filled, same as that terms. Okay, more than half filled, then this is taken as L1 plus S1, or you can say general way L plus S. Okay, this is the J value. Okay, for whenever you are calculating for that magnetic moments, we will take J as like this. Okay, whether that is half filled or more filled. Unlike in that when we are discussing of term symbols, we used to take that L1 plus S1 dot L1 minus S1. So we used to get that more than one values. But whenever we are calculating for that magnetic movements, on that case we will not take more than two values. We will take only one values. So for that, what we will do that we will check that whether this orbit is half filled or fully filled. This is, sorry, whether it is more than half filled or less than half filled, or it is fully filled, or all are half filled. Okay, so whenever it is all are half filled, on that case this value is not needed. The J value is not needed, because that we will discuss after this. Okay, so now we will consider for less than half filled and more than half filled. So here this is the less than half filled, this is less than half filled. Okay, so whenever you are calculating for the magnetic moments, you will not take that L1 plus L2 L1 plus S1 dot L1 minus S1. I will not take. We will take that. We will take whether J is L1 plus S1 or L1 minus S1. Okay, so if it is less than half filled, then this is taken, and if it is more than half filled, then this is taken. Okay, so this is less than half filled, so we take L minus S. Okay, so since this is less than half filled, since it is less than half filled, so J equal to L minus S, that is L1 minus S1. So what the value of L1, that is 5, and this is 1. Okay, so this is going to get the 4. So J equal to 4 we get. Okay, so what are the thing needed? We needed the J value and G value also we need. Okay, how to calculate the G? G is this formula. Okay, so for that we also need that S value. Okay, and we also need that L value. L value we have 5, and S value also we have 1. So from here we can calculate the value of G. Okay, so if I calculate the value of G, that is 3 upon of 2, 3 upon of 2, this constant I will do, that is 3 upon 2, not 2 upon 3, that is 3 upon 2. Okay, bigger than this, that is improper fractions. Okay, plus that is going to be S, first S will come, S plus 1, and in between one negative will come. Okay, that is negative, then L plus 1, after that 2J plus 1. This is the formula for calculating the G value. Okay, so 3 upon 2 plus here S plus 1, in the middle negative will come, after that L plus 1, 2J plus 1. Okay, so for here 3 upon of 2, S value is I think 1 here, in this case S is 1, so 1 plus 1, that is 2, and L is 4 plus 1, that is 5, and 2 J value is oh sorry, L is 5 here. L is 5, 5 plus 1, that is 6, and J value is 4. Okay, J value is 4, 4 and 4 plus 1. Okay, now you do that 3 upon of 2 plus, this is going to be 2, and this is going to be 30, and this is going to be 2 into 4, so 2 power ja 8, 4 1 ja 5. Okay, so this will be solved it, then this is going to be 3 upon 2 plus, this value is be 2.2 minus 30, that is going to be get minus 28, minus 30, that is going to be 40. Okay, so if you solve it, the value 3 upon 2 plus minus 28, that is going to be minus 28 upon 40. So solve it, then what the value will get, that is, let's say this is going to be 40, this is 27, this is 10, so 3 upon 2 minus 7 upon 10, then 5, 15, 10 minus 7 upon 10, that is going to be get 8 upon 10, that is going to be 4 upon 5, 4 upon 5. So this is 4, 5, that is this 8, that G value is going to be get, G value is 0.8. Okay, so if G is 0.8, then we know that for magnetic moment is G root over of, that is J plus 1. Okay, so you know that J value is how much, 4 plus 1, that going to be get the value, that is G, that is 4 1 5, 5 4 20. Okay, so if you calculate it, root over of 20, what is the value, that is for 20, that we can say that 2 the 10 5, that is going to be 2 root 5. Okay, that is the, so G value is 0.8 into 2 root 5. Okay, so if we multiplied it, then we will get that magnetic moments, that is nearly 0.5 values, on that value is I think 3.52 bm. Okay, this is the magnetic moment, or that if that heavier moment, heavier elements is there, then we can calculate like this. Okay, and if it's more than half field, then we will take that L plus S. Okay, so now we will, likewise we can take any other examples, like if there any orbitals, let's say any 4f7 is there. Okay, for that case we can take 1 2 3 5 6 7 4 1 2 3 4 5 6 2 3 4 5 6 7. So for that, let's say this is 4f9, then 1 2 3 4 5 6 7 8 and 9. On that case, similarly we can calculate that fast H, so magnetic movement H, that is G into J plus 1. Okay, so first we will calculate the G value, and G value is 3 upon up to uh, plus S upon S plus 1 minus L plus 1, then 2J plus 1. Okay. So here we can calculate the G value, that is 3 upon of 2 plus S is how much? Here we are having S values, so we can easily calculate that. This will cancel it up, so which are that single unpaired electron only will calculate. So 1 2 3 4 5. Okay, so that is 5 and multiplied by half, that is 5 upon 2, and this is 5 upon 2 plus 1 minus L. This L value is how much we will get? So this is 2. I calculate that L value, that is 2. This is 3 2 1 0 minus 1 2 minus 3. Okay, so this is 3 2 into sorry this is 3 into 2 plus 2 into 2 plus 1. Okay, this will be 0, so this will cancel out. This is minus 1, this is minus 2, this is minus 3. So total value is how much you will get? That is 6 plus 4 plus 1 minus 1 minus 2 minus 3. Okay, so this cancel, so this is minus 5 6, that is 1 plus 4. Total L is going to get 5. Okay, so if L is 5, then 5 plus 1, and J value here, this is more than half filled. So if it is more than half filled, then J is L plus S. Okay. So here L is 5 plus S is 5 upon 2. 1 2 3 4 5 upon 2. Okay, so this is going to be 10 upon 2 plus 5 upon 2, that is going to be 15 upon 2. This is 15 upon 2 into 2, this is 15 upon 2 plus 1. Okay, so if you calculate it, then we will get the G value. Okay, and if you calculate G value, let's say some value H came, some value X, then that after that we will calculate the magnetic moment, that is G root over of J plus 1. Okay, so let's say some value we will get from G, then that is X, let's say. Then this J value is how much? That is 15 upon 2 plus 1. Okay, if you calculate it, then we will get that magnetic moment. Okay, so calculator is allowed, so we can easily calculate it, then we can get that magnetic moment if it's half filled or if it is less than half filled. And let's say if it is fully filled or if it is single filled. Okay, fully half filled. Let's say if it is 1 2 3 4 5 6 7. Let's say 1 2 3 4 6 4 5 6 7. 1 2 3 4 5 6 7, and 1 2 3 4 5 6 7. This value is 3, this value is 2, this is 1, this is 0, this is minus 1, this is minus 2, minus 3, and it is fully half filled. So in this case, L will be, we see that will be going to be 0. Why? Because you see that L, this is 3 into 1 plus 2 into 1 plus 1 into 1 plus 1 into 0 plus 1 into minus 1 plus 1 into minus 2 plus 1 into minus 3. Okay, so this is 3 into 1 minus 1 3 1 into minus 3, it will cancel it up. And let's say this is 2 into 1, this is 2 and minus 1, cancel up. And this is 1 into 1, this is 1 into minus 1, cancel up. And this is 0. So this is, so L value is to get into, you will get that value is 0. Okay, so if L value is 0, then for the case of S value is 7 into half, that is 7 upon 2. Okay, now that whenever you calculate the J value on that case, this is uh, not neither fully less than half filled, neither fully more than half filled, because this is all are half filled. On that case, we know that J values, how is to calculate that? L plus S or L minus S. Okay, both the cases L is 0, then only S value will come. Okay, because L is 0 plus 7 upon 2, and this is in the mode. Or if we say that L 0 minus 7 up 2, this is mode. So here also we will get 7 up 2, here also we will get 7 up 2, because this is the mode is there. So only one value only we will get. So for this case, for all are half filled, on that case J value will be only one value will come, only this value will come. So here there is no thing like L plus or L minus 1, there will be no any confuse, because only one value will come. Okay, so we will get the J value here. After that we can calculate that values, that is magnetic moment, that is G root over of J upon J plus 1. Okay, and this J is 3 upon 2 plus S plus 1. First S will come, then L plus 1, then 2J, J plus 1. Okay, so if you can easily calculate 3 upon 2, and this value is 7 upon 2 plus 7 upon 2 plus 1, and this value is 0. So this is 0 into something 0, and this value is 2, and J value also we will get that J upon 2, because L is 0, so 7 up to 2 plus 1. Okay, so if you calculate it, then we will get not that this is here. Okay, so if you calculate it, we get some values. Let's say G, then we will use that magnetic moments, this G into J values. J value we will get that value is, let's say J value is 3 upon 2, 7 upon 2, this is 7 up to plus 1. So we can calculate that, and then we can get that magnetic moment. Okay, so these are the cases for finding the magnetic moments for heavier elements. Okay, and that three cases, either it may be less than half filled, more than half filled, or it is half filled. Okay, so if it is less than half filled, on that case, if it is less than half filled, then we will take that L minus S, and if it is more than half filled, we will take that L plus S. And if it is fully half filled, then we no need to take, because only one value we will get here. Okay, next we will discuss about that lighter elements. Next topic is for lighter elements. For this is that two for lighter elements. For lighter elements means this is for transition metal complexes. Generally 3D series means 3D series elements, 3D series complexes. 3D transition complexes. Okay, so for this case, what you see that here that whenever they for lighter elements, we are doing what? Calculations of calculations of magnetic moment. Okay, so how to calculate that magnetic moments for the lateral elements, that is three metal complexes. Here what we look that spin orbit coupling is not considered. Why it is not considered? Let's say that whenever this is a metal complexes, so here that this is the orbit, okay? So here that orbit and this is that metal complexes, and another is transition metal. Let's say, sorry, this is now, this is for that ligand. So here this is also rotating. Let's say, so whenever they are come together, then what happens that this metal ligands and metal, this orbit will be get they will be quenching happen. It means that orbital motions will be get zero. Orbital motions becomes zero. Okay, it means IA, that is L equal to 0. So here we will not consider that spin orbit coupling. Okay, means that J value will be not there. Okay, for the lateral elements, IA J value is not come. Okay, J is spin orbit coupling, so that spin orbit couplings we will not get for lateral elements. Okay, so for that calculations of magnetic moments for lateral elements, what we see here that here that according to questions will write how to what actually we will look here what the questions it asks, whether it asks that spin orbit couple only spin only magnetic movements, or it asks whether it has included that orbital contributions, or it has asked that temperature independent paramagnetism. So here that according to questions we will give the answers. So here the three cases may be possible. Three cases that the questions can come. One is, let's say that is for case 1, this is that if asks, it mention that magnetic moment, or it says that free metal complexes, free metal, that is say that for free metal ions. If it is given that on that case that magnetic moments is going to becomes, that is 4s plus 1. This is the formula of magnetic moments if only spin only magnetic moments or free metal ions. If anything is mentioned, then asked to calculate that magnetic moment, then we will use this formula. Okay, and now that what do you mean by that? SU is magnetic moment, and this is a spin of electron. Okay, so now this case what you say that we can simplify, we may see that some other formulas of spin only magnetic moments. What we see that here S is generally for 1, this is what is the value, this is half. Okay, But generally what we used to do that whenever we are counting the electron, we sometimes we actually very convenient to take that instead of half we want to take that one value. Okay, and this value h minus half. Okay, but we are not very convenient to take half value because it will take lot of time while adding. So if you take that one instead of half, then it will be very convenient. So that's why they actually modified this formula like that. This s value for one electrons, okay, for one electrons this s value has that half value. But what I want to take that for one electrons, I want this s value as 1, means I want to take that in one values, because if I taking half half, then for adding it may um, it will not so convenient. So what I do here, that I want to take that one electron value as 1. So what I'll do that here I will do that multiplied, so that is 2s equal to 1. Okay, 2s equal to 1, and this one I will assume as, let's say, n. Okay, it means that select, I'm assume select 2s equal to n. So if n equal to 2s, then n equal to 2s, and that is value is 1. Okay, because I'm not convenient to take that half value, because while adding you can also take this formula. Okay, but if you want very convenient with taking that one value, then we can say that n equal to s is half value for one electrons. So I can take that 2s equal to 1, and let me assume that 2s equal to n. Okay, then can I modify by this to here, then here this is 4s s plus 1. Okay, so I take that n equal to 2s. I want to put the in terms of one electrons, I want to take, now that in one electron I want to take one value, so I will take in terms of n. Then what to do that here for s, so 2s equal to n, then for s is will be 2n. Okay, and here that I want to take everything in terms of n, then this one I can write that n equal to 2s, then s equal to n upon 2. So this value I can put here, n upon 2 plus 1 root over of. Okay, so this if I add it 2n, then this is 2, then this is 2, that is n plus 2 upon 2, this value. So I can cancel it up to 2. So this value is going to get n plus 2. Okay, so this is that magnetic moment. So this is the magnetic moments. And where n equal to number of electrons present. Okay, so if you using this formula, then you will take that, if let's say here one electrons, let's say here one electron present, then you will take that n equal to 1. Okay, but if you are using this formula, that u equal to, then if the same thing is there, then we will take that for s well as we will take that half. Okay, this is half plus 1. Okay, so same thing, that here we are taking that n equal to 1, here we are considering that this is 1. So here if I use this formula, then here what I'll get, that u is equal to, that is 1 electron, so 1 and plus 1, that is 3 root over of, that is root 3. Okay, and if I take here also, then for this case if I use this one in this formula, then I will have to take this one as half. Okay, for this s is half, because for that, and if you do that, then you will get, that is 2, and this is 3 upon of 2, 3 upon of 2, this cancel, again you will get that root 3. Okay, so but if you take this, it is a little bit lengthy, that's why we will modify it into this formula, so that if one electron there, then directly you put that one, then you will consider it. Similarly, if we have that any electrons, 1 2 3 4 5. Let's say we have the electrons 1 2 3, then on that case directly we can put that magnetic moment. If spin only magnetic moment is asked, then what is that? N plus 2. Okay, that is how many electrons in each number of electrons? That is 3. So 3, that is 3. 3 plus 2, that is 5, like that. Okay, that is 15 root over of. If it is like this, if you're using this formula, okay, at this, if or if you're using that this as this, then we have to take that S value as half. So this one value we are taking as half on this case. Then we take that 4 into half, then half plus 1. Likewise, we have to take it, that is 2, and this is going to be 3 upon 2. Then any problems here? That is n is 3, and this is 3 plus 2 5, 15. Okay, here this is 4, this is half. Yes, you have to take, this is how many electrons? So 4 into S value. Okay, now here you have to look that how many electrons are there. Half, half, half. That is half plus half 1 plus half, that is 3 upon of 2. So we have like this, you have to take that 3 upon of 2, because half plus half we have to add all these things. Then that is 1 2 3, 3 upon of 2. Okay, and again you have to do 3 upon of 2 plus 1, because it become a little bit lengthy. That's why you become that shortcut manner. Okay, and here also you get that same value will get, that is 2 into 2, and this is again 5 upon of 2, that is we get that 3 6 into 5 upon of 2, that is going to be 3, that is going to be again 15. Okay, so if you will take this way, it becomes a little bit lengthy. So we will do that directly, this one, and we will get that this value is going to be get 3 electrons. So this is going to be near about 3.8. Okay, so how to get that's why we did this formulas to shortcut it, but actual formula is from here. Okay, this is that actual formula that we have simplified it to that. This is the actual formula. Okay, this is the modified formula. This is that modified formula to calculate that spin only magnetic moment. Okay, this one also you say that whenever we are looking for, this is, we no need to calculate. If spin only magnetic moment only asks, then we no need to calculate. This is very short trick also there. But trick is that whenever that if it is like this, let's say 1 2 3 4 5, let's say one electron there, the magnetic moments we used to calculate that by using that spin only magnetic moment, that is n plus 2. Okay, we used to calculate, that is 1 plus 1 plus 1, that is 3, that is going to be root 3. Okay, and its value is comes the spin only magnetic moment, that is 1.8. Okay, how I am saying that, see that if it is here 5, let's say 2 electrons are there, then here that spin only magnetic moments will be, similarly we will calculate that n plus 2, that is 2, and that is 2 plus 2, that is 4, that is 8. Okay, so that is going to get some values. So this is going to be 2.8. So actually how I'm calculating it. So short trick is that whenever one electron is there, one unpaired electron, so always take one pair unpaired electron, then magnetic spin only magnetic moment is 1.8. If two electrons there, then spin only magnetic moment is 2, just add 0.8. Okay, similarly if 3 electrons are there, then this spin only magnetic moment is 3.8. If 4 electrons are there, 1 2 3 4, then spin only magnetic moment is 4.8. Okay, so likewise you can go it. Okay, so if I says that, you don't need to apply this formula. This short trick is there. If one electrons, if n equal to 1, then spin only magnetic moment will be 1.8. If n equal to 2, then this spin only magnetic moment will be 2.8. And if n equal to 3, then this is going to be value, that is going to be 3.8. If n equal to 4, this value is going to be get 4.8. Okay, similarly likewise, like if it is n equal to, let's say 9, then this value is going to be 9.8. like that wise we can take all the values if it only asks that spin only magnetic moments. Okay, so if spin only magnetic moment is asked, then we use this formula, or we can use that other formula, that is, or we can use that short tricks. Okay, so maximum times only you will not use, you will only, but you know how we have calculated, but actually we use the short tricks, then it will be all answer will be answer, all will be the answered. Okay, so only use the short tricks. Okay, these are the actual formula, but we can use the short tricks. If spin only magnetic moment has asked, or free metal ions is mentioned. Okay, maximum times this will come. This is very important, not this formula, this. Okay, and you use that short tricks if this is asked. Okay, now next, that is another types is that is if it is triply degenerates. Triply degenerates. If it is triply degenerates, it means that T2G is unsymmetrically filled. Okay, on that case, how we will calculate that magnetic moment? T2G unsymmetric field means that we know that d orbitals, how it is. Let's say octahedral case. This here that electrons, if you feel 1 2 3 4 5, let's say 6, this is unsymmetrical, means T2G, this is the T2G, and this is the EG. This is unsymmetrically filled, or that triply degenerates. On this case, that orbital contributions will be there, that L value will be come here. On that case, what will do, that orbital contributions, orbital contributions. So what the formula for the magnetic moment for this case? I will erase other than this. In this case, magnetic moments is calculated the same formula, that is for s plus 1, okay, and that is l plus 1. This is that when that there will be the additions will be there, okay, this two will be added, and this is only spin only, and this is orbital, okay. This because this L represent that orbital angular momentum, so this orbital angular momentum will comes if it is unsymmetrically filled, okay. So on the, this is according to the questions, that way if it is asked to calculate magnetic moment, and that is only spin only magnetic moments, and or it may be written pre-metal ions, then you will not take anything triply degenerate or doubly degenerate, we will not consider anything, we simply calculate it by this way, okay. It may be doubly degenerate, it may be triply degenerate, we will not take any considerations. But if it is not mentioned that spin only magnetic moment or pre-metal ions, on that case we have to take that whether it is triply degenerated or it is doubly degenerated or it is non-degenerate. Okay, so now let's say that magnetic moments, we are going to calculate that magnetic moments. That is transition metal complexes or lateral elements, okay. For this case, if first case that if in questions, okay, if it is asked that spin only magnetic moment or it says that for three metal ions, then use that formula, that is this equal to n plus 2, this formula, or you use that short tricks, okay. This always use the short tricks, okay. That is 1 n equal to 1, then spin only magnetic moment will be 1.8 likewise, okay. If it is asked that spin only magnetic movements or pre-metal ions, but now if it is says that but if not mention that spin only magnetic movement or free metal on the ions, if it is not mentioned, then what you have to do, if it is not mentioned, then we have that two cases, have the two case. First case is triply degenerates, and another is doubly degenerates or non-degenerates. Okay. If it is not mentions anything, okay. If this is case 2, if not mentioned, spin only magnetic movement or free metal ions is not mentioned, then we have that these conditions. One is triply degenerates and it is doubly degenerates case, okay. So if it is spin only magnetic movements or free metal ions, then do not look for doubly degenerate or triply degenerates, that things will not look. If it is not mentioned, then we will look that whether it is triply degenerates or doubly or non-degenerates. Okay, this we will look. So if it is triply degenerates, on that case, what you see that orbital contributions will happen. Okay, I mean that spin only magnetic moment will be that for s plus 1, this is spin, we add that orbital value also, that is l plus 1. This is the spin for this if this is triply degenerates. Okay, so that is, we can also simplify it, that is n plus 2 plus l plus 1 we can use. It means the doubly degenerate means triply degenerate means this type of conditions where this is there, any conditions like this is there or this is there, or it may be like this is there. Any of these conditions we will use. For this case we will calculate that magnetic moment by using this formula. Okay, so if I take these examples, and note that for transitions metal complexes, for this case we no need to calculate that. Okay, first let's calculate that magnetic moment. Okay, so if it is, let's say d1 octahedral, okay, it asks to calculate that magnetic moment like this type. So how will calculate? That is n plus 2 l plus l plus 1. Okay, so here that n is how many electron? 1 electron, so 1 plus this value is going to be get 1.8, so 1.8 and plus this value will be that l value will be how much? So whenever this, for that we no need to calculate this l and all this thing. What is there? Whenever we know that d1 and d9 and d2 and d8, d3 and d7, d4 and d6 and d5, so this we know that the terms are, that is always fixed for d1, always that is d f f ds. Okay, that you have to say that d f f ds, you have to remember this is 2, this is 3, this is 4, this is 5, this is 6. Okay, so from here that this is a d1, so this is terms we will get d2. Okay, this is the terms. So here we understand that this is that d means that we know that 0 1 2 3, l below will be, this is s, b, this is d, this is f, so l value will be that 2. Okay, so no need to calculate this one how much l value will be. Okay, that is, we can directly understand that l value is 2. Okay, and this is 2 plus 1, so if you calculate it, 1.8 plus this is 2 plus 1, that is 3, 2 into 3, that is 1.8 plus that is 6. And so if you calculate it, this magnetic moment, so according to only spin only magnetic movement, the spin only magnetic movements, its value has to come 1.8 because 1 electron. But since this is triply degenerates is there, so orbital contributions also there, so some extra value will come. Okay, so sorry, this is not 1.8, this value is n, so that is 1 plus 1, that is 3. Okay, 2 plus 1 3 1, this is 3, so this is 3, so this value is going to get something like 2.8 some value it will come, some approx value, because here the triply degenerates is there. Okay, so if you calculate only spin only magnetic moment, then we will get that 1.8, but actual value will be, experimental value will be get something 2 to 2.8 or 2.5, like that value will come. Okay, 2 to 2.5 value will come. Likewise, any triply degenerates, any cases if you take, then the value will come like this. Let's say if I take about of that D7 case, D7 case if you take, then let's say 1 2 3 4 5, so this is 1 2 3 4 5 6 7, how it will be d orbitals. So this is, let's say, if you take octahedral, then 1 3, fill the electrons, 1 2 1 2 3 4 5 6 7, this is triply degenerates. So here that if you calculate spin only magnetic movements, then how many unpaired electrons are there? 1 2 3 4 5. Okay, so whenever you are calculating the spin only magnetic movement, that n spin only magnetic movements, that is spin only magnetic movement, that is n plus 2, this value, and we say that shortcut what you have like that, calculate the value of n. So here n of value is unpaired electron, not paired electron. Okay, unpaired electron is 1 2 3 4 5, so 5 unpaired electrons, so spin only magnetic moments will be 5.8. okay, not that 7.8, not that, this is a number of unpaired electrons, 1 2 3 4 5, so that is going to be 5.8. but here since this is triply degenerates, so its value will be nearly 1 2 3 4 5 6 7, so nearly that value will be 6.2 to 6.8, this type of value we will get. Okay, okay. D7, problem with it. D7 case wrong. Oh, sorry. So we have to take that how many unpaired electrons after that splitting, not before splitting. Okay, sorry. After splitting, how many unpaired electrons are there? 1 2 3. Okay, so 3 unpaired electrons, not 5. 3 unpaired electrons are there. So spin only magnetic moments will be only magnetic moment will be 3 are there, so that is 3.8. okay, so if you calculate this is spin only magnetic moment, but here that since this is triply degenerate, the orbital contributions is also present, so that means that its value will be, we have to calculate by using this magnetic moment is n plus 2 plus l plus y. Okay, so we are adding this orbital contributions also. So here we will say that what are the values here, that is we have seen that whenever d1, that I have written here, So D3 and D7, then that will be D3 and D7, then that is going to be 4F, that is 4F. So I will directly write here, since this is D7 or D3 case, then I say that is, we know that from here F 4, we no need to calculate that all that L value, all these things. We directly, if you remember this D F F F DS, then we will easily calculate the terms. That is for F. F means that here how many this represent that, this 4 represent that 2 S plus 1, and F represent that L. What will be the L value? So we no need to calculate this whole these values, okay, because we already know the terms, okay, from that tree. So this is F. So F means 0 1 2 3 4, that is S P D F. So F value is 3, sorry, L value is 3. Okay, from here I know that L value is 3, and here also I know that ampere electron is 3. 3 plus 2 5, plus L is how much? 3, and this is 3 plus 1, that is 4. Okay, this value, that is 15 plus that is 12. So that is going to be 24, then 25, 26, 27. So if you calculate it, then 27, that is 3, that is 3 is to 3. This is going to be get that 3 into some value, that is going to be that nearly, this is 3 point, if you calculate here spin only magnetic mode 3.8, so its value is going to be get nearly about of 4.8 to 5, 8 to 5. Okay, where this is only spin only magnetic moment, then we will get 3.8. But here that since orbital contributions also included, so this effective magnetic movements we will going to get 4.58 to 5. Okay, so you can easily also calculate it, root 3 values into 3, we will get something near about of these values. Okay, so this is the case of if triplet degenerate is there, then you can use these formulas and we can calculate it. So where this is, if that is not mentioned, spin only magnetic movements and free metal ions, if not mentioned, then only you will go for triplet degenerate or doublet degenerate. If it is mentioned spin only magnetic movement or free metal ions, then don't look for this triply or doubly or non degenerate cases. On that case, you will directly calculate spin only magnetic movement by using these short tricks. Okay, now we will go for doubly degenerate cases. How we will go for doubly degenerate cases? Okay, if it is doubly degenerate case, then how will you solve this how will tackle this problems? If it is doubly degenerate, means that the case, like if we say that it is doubly degenerates, this type of things will be there. Three. Okay, so if this is doubly degenerate, it means that this type of electrons 1 2 3 4 like this, or let's say doubly degenerate means here the degenerate state will be here. Okay, or it may be, let's say 1 2 3 4 5 6 7 8 9. Okay, this is the doubly degenerates, or it may be the cases of let's say these the cases 3. It may be like this 1 2 3 4 where non-degenerate cases also here mention that if it is doubly degenerate or non-degenerate, here that non-degenerate cases, these cases, or it may be the tetrahedral cases also, 1 2 3 doubly degenerates, maybe like this type of case. So this all the cases we see that with these cases we will use for, if this type of orbitals are there, then we will use that for calculating magnetic moments. What that is, we will use the formula that is spin only magnetic. This is effective magnetic moment, that is spin only magnetic moments. Spin only magnetic moments, that is 1 minus alpha into lambda upon then splitting energy. Okay, this is that magnetic moments if it is doubly degenerates or non-degenerates are there. Okay, then what is that here spin only magnetic moments? We know that will calculate by n into n plus 2. Okay, and this is 1, and alpha value is, we know that dff ds. Okay, and this is 2, this is 3, this is 4, this is 5, this is 6, and what we know that here that this d and this 2d case, that alpha value is 2, and if this f and f case, this alpha value is 4, and this s case, that alpha value is 0. This you have to remember that this 2d case, dd case, alpha value is 2, and this ff case alpha value is 4, and whenever this s is for s, that alpha value is 0. And what is that for lambda value? That is d1, d2, d3 and d4 case. This lambda value is positive, and for that is d5 value is not needed, that is d6, d7, d8 and d9 case, this alpha value is negative. Okay, negative value will come, and this and delta naught is splitting energy, so you can easily calculate the splitting energy from that. If it is doubly degenerates or non-degenerate case, then for calculating that magnetic movements we will use this formula. Okay, let's say if that example, like if we say that is tetrahedral d power d7 tetrahedral cases. What is there for this case? We see here that tetrahedral, tetrahedral 1 2 3 4 5 6 7. So this is non-degenerates. So non-degenerates or doubly degenerate. On that case, how you will calculate that magnetic moment? So magnetic moments for this case is that, since this is d7. Okay, so we say that d3 or d7, this is f4. Okay, so this is, you know that from there that dff ds. Okay, this is d1 and d9, this is d2 and d8, and this is d3 and d7, that is f. This is 2, this is 3, this is 4, so this is for f4. So this, from here we understand that this is for f4. Okay, now this value is spin only magnetic moments. So spin only magnetic moment is 1 2 3, that is 3 unpaired electrons are there, so 3 means that spin only magnetic moments will be 3.8. okay, so this is going to be that 3.8, and now we'll calculate that one, and that is alpha into lambda, then delta splitting energy. Okay, so 3.8 to 1, and we no need to calculate the terms, so we directly understand that terms is this. Okay, so for transition metal complexes, the for calculating terms is very easy. Only remember this. Okay, so if d1, then the terms is always d2, d1 and d9 case always the terms is d2, and the d2 and d8 the terms is always 3f, so no need to calculate all these things, L value, S value, and calculate the terms. So we no need to do for the transition metal complexes. We simply remember this one, then apply it. D1, D9 always D2, D2, D8 always F3. Okay, this is the terms. Okay, so calculating terms is very easy for transition metal complexes. So we no need to calculate all the L value and S values. Okay, we simply use this trick and understand that. Okay, so if it is D3 and D7, so here D7 case, so the terms is F1. Okay, so we understand that F. So here that is 1 minus this alpha. This alpha is for F case. This is that D3 and this F. So that alpha is, so we say that D F F ds. So this value, that alpha is for, and this values, this D and this D. Okay, alpha is that is 2 and this is 0. Okay, 2 for 0. Okay, so here that alpha is 4 and this is negative, some value they will give. Okay, some negative value will come. After that, splitting energy we can easily calculate here, and that is how much, 1 2 3, this is 1, so this is 0.6, we have to multiply, that is 1 point minus 1.2. so if you calculate it, they will give some alpha value, some negative value they will give. So if you calculate it, after taking after what of the value they will give, okay, so that value is going to get nearly about a 4.5 to 5. Okay, this that effective magnetic field. Okay, if it is doubly degenerate or non-degenerate case, and if it is simply degenerate case, as simply spin only magnetic moment, that is 3.8, because 3 unpaired electron, so that is 3.8. Okay, so this is the how to calculate that magnetic moments, that according to questions you will calculate that what they ask. Okay, so if give that quick summary, then so calculating of magnetic moments. Okay, magnetic moments. Moment. Okay, so that is 3 cases you will calculate. One is for heavier elements, that is lanthanides, lanthanide case, and here spin only, here spin orbit coupling is considered, and its formula is what, that magnetic moment, that is G J plus 1. Okay. J plus 1. This is the formula if it is that values, that is heavier elements. Okay, and this J is 3 upon of 2, that is improper fractions, and 2, that is first S will come, S plus 1, after that negative L, L plus L plus 1, that is 2 J plus 1. This is the cases if that is heavier elements. And now if it is transitions metal complexes, that is lighter elements, that is 3D transition metal complexes, what you do that here spin orbit coupling is not considered. Spin orbit coupling is not considered, and here that two cases are there. First case is that if it is asked specifically, case 1, if asks spin only magnetic moments, or it is written that free metal ions, then spin only magnetic moments is that n plus 2. That is, if n equal to 1, then spin only magnetic moment is 1.8. Is n equal to 2, then that is going to be 2.8 likewise. Okay, and if that is case 2 is, if not asked this other than case 1 asks, means that is it not mentions spin only magnetic moment or free metal ions. If not mentions, okay, if not mention spin only magnetic or free metal ions, then we will go for two case, that is A and B. The first case that triply degenerates, and other can is doubly degenerates or non-degenerates. Okay, so for the triply degenerates, then orbital contributions will be there, that is spin only magnetic movements will be for S, that is I can write, that is n plus 2 n plus l plus 1. This formula I will use. Okay, so and if it is that doubly degenerates or non-degenerate case, their orbital contributions, what is it, that orbital contribution which happen, this is the orbital contributions. Now if it is doubly degenerate case, here that is what I do, that on this case this value will be that effective, that is first is spin only magnetic moment 1 minus alpha lambda, or I can do here for this case effective is spin only magnetic moments 1 minus the splitting energy. Okay, and we know that this alpha is value is for D2, or we can write directly, remember that DFF DS, this is 2, this is 3, this is 4, this is 5, 6. So what D and D, that's alpha is 2, and this F and F, that's alpha is 4, and S is alpha is 0. Okay, and for D1 and D2, D1, D2, D3 and D4, this negative value, this positive value will come, and for D6, D7 and D8, D9, this will negative value will come, which that is lambda value. Okay, that we have discussed. So these tricks we remember that for calculating the magnetic moment. Okay, today up to this, thank you. Oh, sorry, one thing that if it is half filled, then for half filled this lambda will be that is not needed. Why? Because for half filled we see that this alpha value will become 0. Why? Because on that case we see that this value is s equal to t, this if dd is come then 2, if f come then 4, if s come then 0. So we see that whenever that is here I mentions here that let's say, or I can write here directly. So you say that D1 and D9, D2 and D8, D3 and D7, D4 and D6 and D5. Okay, in this case, so the D, F, F, D, S. So this is 0, sorry, this is 2, this is 3, this is 4, this is 5, and this is 6. Okay, so whenever this S6 will come, this is S. So if S, for that we know that L 0, 1, 2, 3, this is for S, this is for P, this is for D, this is for F. So for S, L equal to 0. So if L equal to 0, or here also is right that here also it is written that for S this alpha value is 0. So if alpha value is 0, then while calculating this value is 0, then this value will automatically get 0. Okay, so here no need to calculate this value because this value is already 0 because this is S. Okay, so for half weight that this lambda value is not needed. Okay, so this is the how to calculate that magnetic moment. Okay, so today after this, thank you.